Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. 11 million kilometers from here, there is a rock. It is about 160 meters across, roughly the height of the Great Pyramid. It circles a larger rock, the way a moon circles a planet. And it has been doing that quietly, without interruption, for longer than our species has had a written language. Except it isn't doing it the same way anymore. It is not a natural change. It is not an orbit that drifted. It was moved, deliberately, by us. And it was moved before anyone could be sure it would work, before we knew what the rock was made of, before we had ever seen its surface. The change is 32 minutes. That's it. 32 minutes shaved off a 12-hour orbit. On paper, it sounds like a rounding error. In practice, it is the first time in 4.5 billion years that a human being changed the path of a world. And the researchers are not using words like interesting or unexpected. They are using words like far larger than predicted. They are saying the models were incomplete. They are saying we still cannot fully account for where all of that energy went. This is the story of DART, the Double Asteroid Redirection Test, the mission where NASA drove a spacecraft into an asteroid at 6.1 kilometers per second on purpose. And here is the part the headlines are not telling you. It is not just that DART hit. It is what happened in the seconds after impact that directly affects whether this technique would ever protect you, here, on this planet. It is what is happening to that rock right now, in 2026, that almost nobody is talking about. And it is what arrives at Didymos in December of this year, a date already locked into the calendar, that will tell us whether we actually understand what we did. Stay with me, because by the time this is over, you will never think about a small rock the same way again. To understand why anyone would build a spacecraft designed to destroy itself, you have to go back to a young geologist and a hole in the ground in Arizona. In 1960, a 32-year-old scientist named Eugene Shoemaker was working on a problem that most of his colleagues considered settled and boring. The problem was a crater, Barringer Crater, out near Winslow, Arizona, a mile-wide bowl in the desert with a rim you can walk. For decades, the mainstream explanation was volcanic, a steam explosion, something from below. Shoemaker's job, day after day, was rock chemistry, grinding samples, comparing mineral structures, tedious, unglamorous, repetitive work. He had spent time studying craters produced by underground nuclear tests in Nevada, and he had noticed something. The nuclear craters and the Arizona crater shared a specific structural signature, overturned rock layers, a particular pattern of deformation. Then, working with the chemist Edward Chow, he found the thing that ended the argument. A mineral called coesite, a form of silica that only forms under extreme, sudden pressure, not the slow pressure of geology, the instantaneous pressure of something arriving very fast from above. That was the turning point. Not a launch, not a vote, a mineral in a rock sample. Because once you accept that the crater in Arizona was made by an impact, you have to accept something much less comfortable. That the same thing has happened many times. That it is still happening. That the solar system is not a finished, settled place, and Earth is not standing outside of it. Shoemaker spent the rest of his life on that idea. He co-discovered the comet that broke apart and slammed into Jupiter in 1994, an event humanity watched live, in real time, as a planet took 21 direct hits over 6 days. That was the moment the abstract became visible. Impacts were not ancient history. Impacts were current events. Consider what that meant for people watching in 1994. Jupiter is a target roughly 11 times the diameter of Earth, and the impact scars left by those fragments were, individually, comparable in size to our entire planet. Dark bruises in the cloud tops, visible through backyard telescopes, lasting for months. Nobody had to be persuaded with equations. You could look up and see it. Shoemaker's argument had been that this is not rare. It is simply slow. The solar system is still finishing itself, and the leftovers are still in motion. Earth's own surface hides the evidence. Weather erodes craters. Plate tectonics recycles the crust. Oceans cover most of the record. The moon does not hide anything. Look at the moon, and you are looking at the unedited version of what happens. Shoemaker died in a car accident in Australia in 1997. 2 years later, a portion of his ashes was carried to the moon aboard the Lunar Prospector spacecraft. He remains the only person buried off-world. And in 1998, the year after he died, the United States Congress gave NASA a formal assignment. Find 90% of the near-Earth objects larger than 1 kilometer across. The big ones, the civilization enders. That survey largely succeeded. We now know where most of them are, and none of the known ones are coming. Then, in 2005, Congress extended the assignment downward. Find 90% of the objects larger than 140 meters. That's the class of object that doesn't end civilization. It just erases a region. And that survey is not finished. Estimates have consistently suggested we have found well under half of them. In 2016, NASA formalized the effort into a Planetary Defense Coordination Office, which raised the obvious follow-up question. Suppose the survey works. Suppose we find one and it is coming. Then what? Nobody had ever tested an answer, not once. Every plan for deflecting an asteroid existed only on paper and in simulation. The physics was plausible. The physics was also completely unverified. DART was built to end that. The concept is called a kinetic impactor, and the appeal of it is that it requires no new physics at all. You do not blow the asteroid up. Blowing it up is the worst version of this. Fragmenting a rock into unpredictable pieces on unpredictable paths turns one solvable problem into 100 unsolvable ones. Instead, you nudge it. Here is the chain, one step at a time. An asteroid on a collision course is not aimed at Earth the way a bullet is aimed. It is on an orbit, and Earth is on an orbit, and the two orbits intersect at a particular moment, years in the future. Change the asteroid's speed by even a fraction of a millimeter per second, and over years, that tiny difference compounds. The rock arrives early, or late, and Earth is somewhere else. You do not have to move the asteroid out of the way. You have to move it out of the appointment. So you hit it with mass moving fast. Momentum transfers. That's the first part, and it is simple bookkeeping. 570 kilograms of spacecraft, traveling at 6.1 kilometers per second, delivers a specific and calculable amount of momentum into the rock. But that is not the whole story, and the second part is where it gets interesting. When you strike a rocky surface at 6.1 kilometers per second, you do not just push, you excavate. Material blasts off the surface and away from the impact site. Rock, dust, gravel, boulders. Those ejected fragments do not simply vanish. They carry momentum too, and because they are flying away from the asteroid, they push back against it. The same principle as a rocket exhaust. The asteroid becomes, for a few seconds, its own thruster. So the total push is the spacecraft's momentum, plus the recoil from everything that gets thrown off. Scientists call that multiplier beta. If beta equals 1, all you got was the spacecraft. If beta equals 3, the ejecta tripled your effectiveness. And here is the honest problem. Nobody could calculate beta in advance. Because beta depends entirely on what the asteroid is made of, and we did not know what the asteroid was made of. A dense, solid rock throws off very little material. A loose pile of rubble held together by almost nothing might absorb the hit like a sandbag, or might spray material everywhere. The predictions spanned a wide range, and the honest scientific position before impact was that the outcome was uncertain by a large factor. That is why DART had to be a real experiment and not a simulation. You cannot compute your way out of not knowing what something is made of. And there is one more reason the kinetic option was the one worth testing first. It is the only deflection method that requires nothing we do not already have. No new propulsion. No nuclear device in space, with all the legal and political weight that carries. No decade-long station-keeping mission using gravity to tow a rock, which has been proposed and is elegant and has never been anywhere near a launch pad. A kinetic impactor is a spacecraft, a launch vehicle, and a guidance system. Every part of that already exists and has existed for decades. The only question was whether the physics behaved the way the equations promised when applied to a real object, at real speed, at real distance. That question is what $325 million bought. Now, the hard part. DART launched on the 24th of November, 2021, from Vandenberg Space Force Base in California. The spacecraft was about the size of a vending machine, with 2 roll-out solar arrays that unfurled to roughly 8.5 meters each. Total cost of the mission, roughly $325 million. For a spacecraft whose entire purpose was to stop existing, the target was a 2-body system, Didymos, the primary, about 780 meters across, spinning fast, 1 rotation every 2 hours and 16 minutes, and orbiting it, the small one, Dimorphos, about 160 meters across, completing one lap every 11 hours and 55 minutes. Neither of them was a threat to Earth. This needs to be said clearly, because it was the single most misreported element of the mission. Didymos and Dimorphos were not coming for us. They were never coming for us. The impact did not and could not put them on a course toward Earth. They were chosen precisely because they were harmless, and because the pairing made the measurement possible. That last point is the clever part. Measuring a tiny change in an asteroid's orbit around the Sun would take years of tracking and enormous precision. But measuring a change in a small moon's orbit around its parent is far easier. You watch from Earth. Every time Dimorphos passes in front of Didymos, the combined brightness dips. Time the dips, and you know the orbital period to within seconds. So the experiment had a built-in stopwatch. The minimum threshold for success was set at 73 seconds. Change the orbital period by at least 73 seconds, and the mission counts as a demonstration. Now the constraints. At the moment of impact, DART was 11 million kilometers from Earth. Light takes about 38 seconds to cross that distance in one direction, which means a round-trip command and response takes over a minute, and in the final phase, everything was happening in seconds. So nobody flew this. Nobody could. The final 4 hours of approach were handled entirely by an onboard autonomous navigation system called SmartNav, working from a single camera called Draco. No backup, no second attempt, no repair. One spacecraft, one target, one chance. And here is the constraint that makes the whole thing genuinely absurd. DART had never seen its target, not once. Dimorphos had never been resolved as anything more than a point of light. Its size was inferred from brightness, its shape was unknown. Its position within the system was known statistically, not precisely. For most of the approach, Draco could see Didymos, the big one, as a single dot. Dimorphos was hidden inside that dot. The spacecraft had to fly toward the pair, wait for the two objects to separate visually, correctly identify which one was the smaller moon, lock onto it, and steer into it. That separation happened roughly 50 minutes before impact. 50 minutes. On a mission that took 10 months to arrive. The spacecraft spent 10 months flying toward a target it could not distinguish, and then had 50 minutes to find it, choose it, and hit it, while closing at 6.1 kilometers per second, with Earth over a minute away and completely unable to help. There is one more thing worth noting about that camera. Draco was not just the navigation sensor, it was also the entire science payload. One instrument, doing both jobs, because there was no room and no mass budget for redundancy. If Draco had failed at any point in those final hours, the mission would have flown past its target, and there would have been nothing to show for 4 years of work. The spacecraft also carried a demonstration of a new ion propulsion system called NEXT-C, and rollout solar arrays being tested for future missions. Technology development riding along on a vehicle scheduled for deliberate destruction. Everything on board had a deadline measured in months. In the final hour, Draco started sending back images at roughly 1 per second. And a world that had never been seen came into focus in real time, on screens at the Johns Hopkins Applied Physics Laboratory, in front of the people who built the thing. Dimorphos was not smooth. It was a heap of boulders, a surface of loose, jumbled rock, some of the individual stones several meters across. The final complete image was taken from about 12 kilometers out, showing a patch of that boulder field. Then one more image began to transmit, and cut off mid-frame, because there was no longer a spacecraft to finish sending it. Impact, the 26th of September 2022, at 23:14 Universal Time. The mission threshold was 73 seconds. The measured result, announced by NASA about 2 weeks later, was 32 minutes. Let that land. Not 73 seconds. 32 minutes. The orbital period of Dimorphos dropped from 11 hours and 55 minutes to about 11 hours and 23 minutes. Later refinement, using more observation data, put the change at roughly 33 minutes. That is more than 25 times the minimum success criterion. Here is the plain language version. Imagine a runner circling a track once every 12 hours, on a perfectly consistent schedule. For millennia, you shove them once, sideways, and from that day forward, they complete every lap half an hour early, permanently. The measurement itself came from telescopes on the ground, watching the brightness dips, plus planetary radar. The orbit was smaller now, tighter, faster. Dimorphos had been pushed inward, toward its parent, and that number, 32 minutes, immediately told the science team something they had not been able to determine any other way. Because the spacecraft alone, 570 kilograms at 6.1 kilometers per second, could not have done that. Not by a factor of several, which means the ejecta did most of the work. There was a witness. 15 days before impact, DART released a small companion, Lycia Cube, a briefcase-sized CubeSat built by the Italian Space Agency. It carried no propulsion for the encounter. It simply coasted behind, on a slightly offset path, timed to arrive a few minutes late. Its job was to survive the moment DART could not. Lycia Cube flew past the system roughly 3 minutes after impact, passing within about 57 kilometers, and photographed what was happening from the side. What it saw was not a crater with a puff of dust. It was a structure. Long, bright filaments of debris, streaming away from Dimorphos, in complex, branching patterns, curved streamers, a plume, with architecture. Meanwhile, telescopes across Earth and in orbit were watching the same thing from 10 million kilometers away. Hubble tracked a tail of ejected material that stretched to over 10,000 kilometers in length. Then, remarkably, it split. Hubble recorded a second tail forming. The asteroid had grown a double tail, behaving less like a rock and more like a comet. For a short period after the impact, this thing was, by appearance, one of the brightest small objects in that region of the sky. Observers on the ground could see the system brighten sharply and then take weeks to fade. Here is the scale comparison that makes it real. A vending machine-sized spacecraft hit a rock, and the resulting debris cloud stretched out longer than the distance from Earth to the Moon, several times over, and the mass involved was substantial. Analysis published in 2023 estimated that the impact ejected on the order of 1 million kilograms of material off the surface. Compare that to the 570 kilograms of spacecraft that started it. You threw a vending machine. You got a mountain's worth of gravel in return. That ratio is why the orbital change was 32 minutes and not 73 seconds. So the multiplier, beta. The papers published in the journal Nature on the 1st of March 2023, led by teams including Christina Thomas, Andrew Cheng, Tarek Daly, and Jianyang Li, put the momentum enhancement factor at roughly 3.6, with a meaningful range around it depending on the assumed mass of Dimorphos. Keta of 3.6 means this. For every unit of push the spacecraft delivered directly, the asteroid received about 3.6 units total. The recoil from the ejecta contributed the majority of the deflection. And this is where a good documentary has to be honest. That number is not a clean measurement. It is an inference. It depends on the mass of Dimorphos, and the mass of Dimorphos is not directly known. It was estimated from assumed density and estimated volume. Change your density assumption, and beta moves. This is the single largest open question left over from DART. Not, did it work? It worked. The question is, why it worked as well as it did, and whether that would repeat. Because the answer appears to come down to composition. Dimorphos was a rubble pile, a loose aggregate of rock and gravel held together largely by its own extremely weak gravity, with very little internal strength. A solid, coherent boulder would have resisted. It would have cratered locally and thrown off comparatively little. A rubble pile did the opposite. It gave way, and in giving way, it launched an enormous amount of its own material into space, and that material pushed back. The uncomfortable implication, DART's spectacular result, may be a property of that specific asteroid, not a general property of the technique. Point a kinetic impactor at a denser, more solid object, and beta could be much closer to 1. The deflection could be a fraction of what we saw. Researchers state this plainly. One test on one rubble pile is one data point. Then there was something nobody planned for. In 2023, astronomers using Hubble, work led by David Jewett, identified 37 distinct objects moving slowly away from Dimorphos. Not dust, boulders. Estimated sizes ranging from roughly 4 meters to 22 meters across. They were drifting away at speeds of only a few kilometers per hour, walking pace. A swarm of house-sized rocks, casually leaving. These were almost certainly not fragments broken off by the impact shock. The leading interpretation is that they were already sitting loose on the surface, part of that boulder field Draco photographed in its final seconds, and the impact simply shook them free. Later analysis of the Lycia Cube imagery, published in 2024 by a team including Tony Farnham, identified over 100 boulders thrown off in the immediate aftermath, some moving considerably faster, and found that their distribution was not random. The material came off in clustered, directional patterns rather than an even spray. That matters more than it sounds. If ejecta comes off in a preferred direction rather than evenly, the recoil push has a direction too, and it may not be the direction you aimed for. For a real deflection mission, where you need to know precisely how much and precisely which way, an asymmetric, clumpy, partly unpredictable ejecta pattern is a serious complication, and there is a longer consequence. Those boulders are now on their own orbits. Some analyses have suggested that a portion of the ejected material could eventually cross the orbit of Mars, arriving over timescales of thousands of years. Nothing dangerous, nothing that reaches Earth in any hazardous form. But it is worth stating plainly, the debris did not simply fall back. Some of it left, and it is still going. We did not just move an asteroid, we scattered a small amount of the solar system's furniture, and we are not entirely sure where all of it ended up. There is one more consequence of the boulder swarm that deserves stating. Those 37 objects, drifting at walking pace, are gravitationally almost free. Some of them may remain loosely associated with the Didymos system for a long time. Others will not. And every one of them carries momentum that came out of the impact. Momentum that the deflection calculation has to account for, and largely could not, because nobody predicted a swarm of house-sized rocks would be part of the outcome. This is the recurring lesson of the entire mission. The parts we could calculate, we calculated well. The trajectory was correct. The timing was correct. The targeting worked to within meters after 10 months of flight. What we could not calculate was what the asteroid itself would do in response. And the asteroid did considerably more than the models expected, in ways we are still cataloging 4 years later. The last finding is the strangest, and it is the one that most directly undermined the pre-impact assumptions. The models going in largely treated this as a cratering event. Spacecraft arrives, excavates a crater some tens of meters across, throws out material, done. The asteroid ends up mostly the same object with a fresh hole in it. Subsequent modeling work suggested something different. If Dimorphos was as weak and as loosely bound as the evidence indicates, then the impact may not have made a crater in any conventional sense. It may have deformed the entire body, reshaped it, turned an object that was roughly one shape into a measurably different shape, flatter, more elongated, by rearranging its whole structure. Think about the difference. A bullet into a wall leaves a hole. A fist into a pile of sand does not leave a hole. It moves the pile. There is also evidence that the impact disturbed Dimorphos's rotation. Before, it was almost certainly tidally locked, one face permanently toward Didymos, like our moon toward Earth. After, the data are consistent with the object tumbling, its rotation no longer settled, wobbling as it goes. And some of that ejected material never escaped. It went up slowly, and gravity, however feeble, pulled a portion of it back down onto the surface over the following hours and days, resettling into a new configuration. So the honest summary of what we did is not NASA cratered an asteroid. It is closer to this. We hit a loosely bound pile of rock hard enough that we changed its orbit, changed its spin, changed its shape, and stripped material off it that is still traveling. And researchers still cannot fully explain the detailed mechanics of how all of that energy was partitioned. 32 minutes. 570 kilograms, 6.1 kilometers per second, 11 million kilometers away, with nobody flying it. Which brings us to what happens next, and it is not hypothetical. On the 7th of October, 2024, the European Space Agency launched a spacecraft called Hera. It is heading to the exact same place. Didymos and Dimorphos. Its arrival is scheduled for late 2026, December, that is this year. Hera is the audit. DART was the punch thrown blind. Hera is the examination afterward. It carries instruments to do the things DART could never do, because DART's entire mission ended at the moment of contact. Hera will measure the mass of Dimorphos directly, by observing how its gravity affects the spacecraft's trajectory. That single measurement collapses the biggest uncertainty in the entire experiment. With a real mass, beta stops being an inference with a wide error bar and becomes a number. It will survey the surface and determine what the impact actually did. Crater, or global reshaping. It carries radar intended to probe below the surface, the first attempt to look inside an asteroid and see how a rubble pile is actually assembled. It carries 2 CubeSats of its own, and the plan calls for one of them to attempt a landing on Dimorphos at the end of the mission. And here is what that produces. Right now, kinetic impaction is a technique we have tried once, successfully, on an object we did not understand, with results we cannot fully model. After Hera, it becomes something closer to engineering, a calibrated tool with known behavior and known failure modes. That distinction is the entire point. Because the survey work continues, new objects in that 140-meter class are still being cataloged, and a substantial fraction of them have not been found yet. The value of DART is not that it saved anyone. It is that, if a real one is ever identified with enough warning, the response would not begin with a blank sheet of paper. But note the phrase, enough warning. A deflection like this requires years to decades of lead time for the tiny velocity change to compound into a miss. The technique does not work on something discovered next month. It works on something discovered next decade, which means the real defense is not the spacecraft, it is the telescopes. The finding is the hard part. The hitting, we have now demonstrated, is comparatively easy. So what does all of this actually add up to? One spacecraft, 570 kilograms, 6.1 kilometers per second, 11 million kilometers from home, with no one at the controls and no second attempt. 32 minutes taken off an orbit that had run undisturbed since before there was anything on Earth that could count minutes. Every one of those numbers is real, measured, and published. And Dimorphos is still out there, tumbling slightly, reshaped, moving on a path we gave it, trailing rock that will be traveling long after everyone watching this is gone. There are estimated to be tens of thousands of objects in that size class in near-Earth space, and we have found fewer than half. Each one is a rubble pile, or a solid body, or something in between, and we do not know which, for almost any of them, until we look. We have proven we can hit one. We have not yet proven we can predict what happens when we do. Hera arrives in December. It is genuinely worth wondering what it is going to find. If you want the answer when it comes, subscribe and turn on notifications, because this channel covers real space discoveries, grounded in real published research, rather than exaggerated headlines.